Hello. In this video, we will address the question of uncertainty. As we have seen, science is incapable of providing certainty because it is based on observation and reasoning. Physical reality, however, cannot be reflected by our senses and our thoughts. To quote Professor Pilke Jr., a scientist who supports the global warming thesis, in our research on the plausibility of IPCC scenarios, we have discovered that the entire set of baseline scenarios used by the IPCC is implausible. In some ways, this is unsurprising. As events unfold in a complex world, even the near-term futures anticipated by scenarios will drift away from reality. Indeed, this is not surprising, since everything is part of a whole, but of a whole that is not reducible to the sum of its parts, where nothing can be explained independently of this whole, yet where each part plays an important role in its own right and reflects this whole in different ways. The whole is infinite, yet at each instant we can only know a finite number of things. This is why our image of reality is necessarily approximate. The parameters describing a phenomenon are infinite in number, so most of them cannot be taken into account. For example, according to Dr. Judith Curry, an eminent climate specialist, future warming runs the risk of overestimating warming over the next 2 to 3 decades if they do not take account of multi-decadal climate variability such as the Atlantic multi-decadal oscillation, which will be shortly entering its cold phase, or if they do not take account of volcanic eruptions. Indeed, the latter are left out in climate scenarios because they are unpredictable. However, due to the direct radiative effect of aerosol particles reaching the stratosphere, large volcanic eruptions lead to a global decrease of mean surface temperature. And this can last over decades or even centuries. All the more so, only a tiny fraction of the parameters governing a phenomenon can be quantified. And among these, only a very small number can be taken account of because we are incapable of solving equations with too many parameters. Mathematical models are based on approximate measures. They are based on an idealized and simplified vision of reality. For example, dimensionless points do not exist in our physical reality. They are an idealization by the human mind of particles that do have dimension. Then mathematical accuracy has to be retranslated for application purposes in our studies of the physical world. And this again results in approximations. For example, we have to decide to what degree of decimal precision we want to transcribe abstract concepts such as square root of 2, 1.4, 1.41, 1.414, or more. We may be driven by a quest for truth, But we must remember that science is not about truth, or if it is, we can never know that it is so. What our ever-deepening scientific understanding does is steer us away from untruths. Scientific knowledge, although the least fanciful form of knowledge, is at best uncertain. Despite our ingenuity to circumvent the problem, we are obliged to confront the question of uncertainty, the scale of which increases the closer we get to human phenomena. The language of mathematics used in science is based on two-variable logic. This means a statement is either true or false. In other words, this language is unable to render uncertainty. To do so, we have invented within the context of this language the theory of probability. But can this theory truly tackle uncertainty? Its applications necessarily suffer from the shortcomings of mathematization, but they bring in their own set of problems. In other words, they are themselves a question of uncertainty. In particular, they are a matter of interpretation. The most common interpretation assumes that individual outcomes have the same probability, an excellent example of a hidden assumption. For example, in thermodynamics, it is assumed that a molecule has the same probability of being in any possible location in a gas. However, this assumption might be rather unrealistic, in which case our mathematical models would be all the more approximate. In other contexts, probability is best interpreted as frequency. In other words, as the proportion within a sample having a given property, namely the ratio x over q, where x is, for example, that number of peas with round seeds in a sample containing a total of q peas, fertilized by peas with round seeds and peas with wrinkled seeds. This is the interpretation more generally used in genetics, but it too is based on assumptions and has problems. Experiments cannot be repeated infinitely. Hence, we are forced to assume that were they repeated over and over again, the relative frequency would attain a definite value. More precisely, the probability is defined as the limit value the ratios x over q tend to as q increases. Now, there are two ways to proceed to estimate this value. There is the scientific approach, which consists in inferring this value based on a large number of ratios estimated experimentally. However, this method faces the main problem that plagues science, namely that of inducing based on a finite number of data. Or else we can proceed mathematically. So what we have are ratios x1 over q1, x2 over q2 for sample sizes Q1 smaller than Q2, and so on. And what we want to find is a curve that extends endlessly, passing through these points. In other words, we want to compute the limit of the function f of q equals x over q as q becomes larger and larger. However, the problem is that there are many curves passing through any given finite number of points. Hence, this process is approximative. Now, the further problem we face is that the result obtained mathematically and the result obtained scientifically may not be the same. However, both methods contain uncertainties, and a priori we cannot tell which one is more appropriate. And this can evidently result in serious problems. If probabilities in the case of events repeatable as many times as desired raise so many questions, then the attribution of probabilities to events that have rarely occurred, possibly occurred only once, or may have never occurred, is even more problematic. We cannot, in these cases, use a frequency interpretation. We cannot also assume the equality of probabilities, since we cannot know that such phenomena present any regularities. Hence, in these cases, what is done is to assign a probability value subjectively based on a personal assessment of a future event. Until the event has occurred, there is absolutely no way of verifying the quality of the assessment. After the event has occurred, its certainty is total. However, this does not imply that the probability value assigned before its occurrence was in any way realistic. These assessments, therefore, do not belong to the sphere of science, but they are given the veneer of scientific respectability and apparent objectivity. For example, in 1979, there was a nuclear accident, the 3-mile nuclear accident in Philadelphia in the United States. Before its occurrence, it was estimated that the meltdown of a core of nuclear reactor was 1 in a million. After its occurrence, given that it was seen that there was meltdown had become absolutely certain. That means with probability 1. So perhaps in the case of rare events or one-off events, we should be prudent and perhaps just stick to qualitative assessments and not try to find quantitative probability values. Or even better, perhaps we should not put our future into the hands of experts. This brings us to the question of unpredictability. Approximations usher in unpredictability even when the differences are tiny. Take a particle moving along a straight line between two walls without any force acting on it. And the particle, each time it reaches an extremity, is reflected back. Because of the errors in the initial measurement of its position and velocity, the difference between the predicted and therefore calculated position of the particle and its actual real position on the line increases with time. And beyond a certain time t that can be exactly calculated, this difference is greater than the length of the line. In other words, beyond a certain time, its position becomes unpredictable. The particle can be anywhere on the line. We can improve the quality of our measuring instruments and therefore reduce the inaccuracies of measurement, but we can never get rid of them. In other words, all we can do is expand the time interval within which a prediction is more or less possible. This example concerns a very simple, idealized closed system. In reality, innumerable factors are involved, adding to the unpredictability. Besides, this example also concerns a deterministic system. In other words, a system which is fully determined by its initial conditions. Even in this case, as we see, tiny errors can propagate and grow. For example, the coded way in which a computer deals with internal calculations includes rounding errors. Errors also occur when the resulting coded language is reprinted on the screen. The situation could be even worse. The system may not be determinable, even if we could exactly know all the parameters at a given instant. This is, for example, the case with the climate because of the so-called butterfly effect. The flapping of a butterfly's wings may cause tremendous effects. For example, a tornado may be formed at the other end of the world, or on the contrary, it may produce no effect at all. We cannot know because such a system is described, unlike the previous example of the particle, not by linear equations, but by nonlinear equations. This is why we have to remain very prudent with long-term weather forecasts or even short-term ones. This unpredictability is not surprising, but it does make predicting difficult, even unrealistic, especially regarding such complex systems as the climate. As Hannah Arendt wrote, predictions of the future are never anything but projections of present automatic processes and procedures, that is, of occurrences that are likely to come to pass if men do not act and if nothing unexpected happens. Every action, for better or worse, and every accident necessarily destroys the whole pattern in whose frame the prediction moves and where it finds its evidence. This is all the more so as the present is itself uncertain. Uncertainty and unpredictability are what makes us human, what gives us a certain degree of free will. They are the source of both hope and fear. We will address these subjects in subsequent videos. Thank you.